Hi everyone. Welcome to the second part of our lecture on 2D drawing representation. In this session, we'll dive into three important aspects that bring clarity and consistency to technical drawings: drawing standards, dimensioning practices, and ANSI drawing views. These elements ensure that our drawings are not only accurate, but also universally understood across teams, industries, and countries. By the end of this part, students should be able to identify and apply standard drawing practices, including proper dimensioning techniques and ANSI drawing views, to produce clear and standardized technical drawings. Let's start our lecture by looking at the drawing standards adopted by various countries around the world. Each country often has its own organization that sets the rules and guidelines for engineering drawings, such as paper sizes, dimensioning styles, line types, and symbols. These standards help ensure consistency, clarity, and accuracy in communication between designers, engineers, and manufacturers. For example, in the USA, the standard used is ANSI, which stands for the American National Standards Institute. Japan follows JIS, or the Japanese Industrial Standards, while Germany uses DIN, which stands for Deutsches Institut für Normung, the German Institute for Standardization. In the UK, BS or British standards are followed, and Australia uses AS, which refers to Australian standards. Meanwhile, Thailand has its own standards body known as TC, stand for Thai Industrial Standards Institute, and at a broader international level, we have ISO, the International Standards Organization. ISO standards are often adopted in global industries to facilitate international collaboration and compatibility. Now that we've identified the different drawing standards used in various countries, let's take a closer look at how these standards define sheet sizes for technical drawings. On this slide, we're comparing two of the most widely used systems: the ANSI sheet size system, which is commonly used in the United States, and the ISO sheet size system, which is adopted internationally, including in Malaysia. Let's start with the ANSI system on the left side. ANSI sheets are labeled alphabetically from A to E, where A is the smallest and E is the largest. For example, ANSI A is typically used for standard reports and printouts, about the size of regular letter paper, while ANSI E is used for large format drawings like architectural or engineering plans. Each size is scaled either by doubling or having the dimensions depending on orientation. So if you fold an ANSI D sheet in half, you get the size of an ANSI C sheet, and so on. Now, shifting over to the ISO standard on the right, this system uses the A-series sizes, starting from A0 as the largest sheet. What's unique about the ISO system is its aspect ratio of √2:1, which allows each size to scale down or up perfectly. For instance, A1 is half the size of A0, and A4 is half the size of A3, making it very efficient for printing, copying, and scaling. That's why ISO is the preferred standard for most international design and manufacturing practices. There are two main types of sheet orientations used in technical drawings: Type X and Type Y. Type X is commonly used for sheet sizes from A0 to A4 and follows a landscape orientation, where the width is longer than the height. In this layout, the drawing space is centered within the sheet, surrounded by border lines, and the title block is placed in the bottom right corner. This format is widely used for larger drawings that need to fit more technical details. Type Y, on the other hand, is used exclusively for A4 size sheets and is set up in portrait orientation, where the height is greater than the width. Similar to Type X, it includes a drawing space and a title block, but the layout is more vertical and better suited for compact documents or smaller technical reports. On the right side of the slide, we see a detailed layout of a standard drawing sheet. This includes important elements like the title block, drawing space, and frame lines. Margins are set to specific widths, usually 20 mm for A0 and A1 sheets, and 10 mm for A2, A3, and A4 sheets, ensuring consistent spacing across different paper sizes. Additional features like grid reference borders, trimming marks, and orientation marks help guide printing, cutting, and referencing within the drawing. These standards ensure clarity, consistency, and professionalism in all technical documentation. Now let's talk about drawing scale, a very important part of technical drawings. Basically, a drawing scale is the ratio between the actual size of an object in real life and the size that we show in the drawing. This is super useful because some things, like buildings or machinery, are too big to draw at actual size on a piece of paper. On the other hand, some things, like tiny screws or electronic parts, are too small to see clearly unless we enlarge them. So, why do we use drawing scales? There are three main reasons. First, it helps us fit large objects onto standard-sized paper like A3 or A4. Second, it lets us enlarge small objects so we can show more details clearly. And third, it helps us keep the measurements accurate, even when we change the size of the object in the drawing. When using a scale, we always write the word scale followed by a ratio. For example, scale 1:1 means the drawing is the same size as the real object. This is called full size. Scale 2:1 means the drawing is twice as big as the actual object. This is an enlargement. Scale 1:2 means the drawing is half the size of the actual object. This is a reduction. No matter what scale is used, the dimension numbers in the drawing, like length or width, always show the actual, real-life size of the object. So, if something is 6.5 mm in real life, that's the number that will appear in the drawing, even if the picture is smaller or larger. For example, if you are designing a pen that is 6.5 mm in diameter, but you draw it at half size, ratio of 1:2, the image of the pen will look smaller, but the label next to it will still say 6.5 mm. This ensures everyone reading the drawing knows the true size of the part. Using scales correctly helps designers, engineers, and manufacturers understand and communicate clearly, no matter how big or small the product is. Let's continue by looking at the types of lines used in technical drawing. This part is very important because every line you draw has a meaning. It tells the viewer something about the object. Think of these lines as a visual language that helps communicate features like edges, hidden parts, center points, and even movement. If we use the wrong type of line, it could confuse whoever is reading the drawing, whether it's another designer, engineer, or manufacturer. First, we have the drawing line, also called the visible or object line. This is a thick, solid line, and it shows the parts of the object that you can actually see. For example, the outer edges of a block or the visible part of a hole. Next is the hidden line, which is a thin dashed line. This is used to show edges that you can't see from the outside, like a hole inside a box or the back edge of a part that's blocked by another part. Then we have the center line, which looks like a thin line with long and short dashes. This line shows symmetry in the center of things like holes or cylinders. You'll also see it used to mark the axis of rotation or middle point of circles. The phantom line is made up of a pattern like long dash, long dash. This line is used to show alternate positions or movement, for instance, if a door swings open or a part shifts back and forth. It's useful in motion studies or exploded views. Break lines are used when you want to show that a part is cut short in the drawing, maybe to save space or because the full length isn't necessary to understand the part. These are wavy or zigzag lines. Next, the cutting plane line is a thick dashed line with arrows at each end. This line shows where an object has been cut to show a cross-sectional view. The arrows point in the direction you're looking into the object after the cut. Then we have dimension lines, which are thin lines with arrowheads. These lines show exactly how long, wide, or tall a part is. They connect between extension lines, and the dimension number is placed above a line to indicate the actual measurement. Lastly, leader lines are thin lines with arrows or dots. These point to a specific feature and usually come with a note, label, or symbol. For example, a leader might point to a hole and include a note that says diameter 10 mm, drill through. By understanding and using these different lines correctly, you can make your technical drawings clear, professional, and easy to interpret. No need for extra explanations, because the lines speak for themselves. This slide shows how different types of lines are used together in a single technical drawing. It helps us understand how each line communicates different information clearly and accurately. For example, the visible line shows the outer edges of the object that we can see. The hidden line shows parts that are not visible from the outside, like holes or cuts inside. The center line marks the center of circles or symmetrical parts. Dimension lines with arrowheads show the size or measurement of a feature, while extension lines stretch from the object to help show where the dimension starts and ends. The leader line points to a feature and usually comes with a note or symbol. We also have cutting plane lines, which show where the object is cut to view the inside, as you can see in section AA. Phantom lines show alternate positions or motion paths. Break lines are used to cut out a part of the drawing when it's too long to show completely. Geometric dimensions and tolerances, GD&T, a system used in technical drawing to control and describe the shape, size, and allowable variation of parts in manufacturing. GD&T helps ensure that a part functions properly, even if there are small differences during production. Let's start with the general dimensioning symbols on the left side. These are shorthand notations like for diameter, R for radius, SR for spherical radius, and PL for places. In the middle table, you can see how the American, ASME, and International, ISO, standards compare. Most symbols are similar, like for diameter, but some terms vary slightly. For example, ASME uses controlled radius as CR, while ISO doesn't use a specific symbol for that. It's important to be familiar with both systems, especially when working with international designs or manufacturing. On the right side of the slide, we see a colorful chart that groups different types of geometric tolerances based on their function. These tolerances are important because they define how much variation is allowed in the shape, position, or orientation of features in a part, ensuring parts fit and function correctly in real-world applications. The blue section, labeled Form, relates to the shape of individual features without reference to other features. This includes tolerances such as straightness, which ensures that a line or edge doesn't curve or bend, and cylindricity, which makes sure a cylinder is both round and straight along its length. These are especially important in parts that slide, rotate, or must fit precisely into other parts. Next, in the green section, we have profile tolerances. These control the shape or outline of features, either a line or a surface. This category is useful when the design involves curves or complex surfaces. For instance, if a car body panel must follow a specific aerodynamic contour, profile tolerances will ensure that the manufactured shape closely follows the intended design. The yellow section covers orientation tolerances. These ensure that one feature is correctly angled relative to another. For example, perpendicularity guarantees that one surface meets another at a 90-degree angle, which is important in assemblies like mounting brackets or machine parts that need proper alignment to function correctly. Finally, the orange section includes location and runout tolerances. These deal with how accurately features like holes, slots, or circles are positioned. Position ensures that holes are drilled exactly where they should be. Concentricity ensures that circular features share the same center point, while runout controls how much a rotating object wobbles. These are especially critical in rotating parts like shafts, gears, or wheels, where imbalance can cause failure or vibration. These GD&T symbols make it possible to communicate complex requirements clearly, without long explanations. So, instead of writing a paragraph, an engineer can just place a symbol, like the one for flatness or perpendicularity, and everyone on the production line understands what's needed. In technical drawing, dimensioning is the process of adding measurements to your sketch or CAD drawing to show the exact size, shape, and location of features on a part. For example, if you're designing a metal bracket, you'll need to specify the length, width, thickness, hole diameters, and where those holes are located. Without proper dimensions, the person manufacturing the part won't know the exact specifications to follow. Clear and correct dimensioning is very important for both manufacturing and quality inspection. It helps avoid confusion and ensures that the final product matches the design exactly. A helpful rule to remember is to always ask yourself, what information is needed to make this object? You only need to include the necessary details, not more, not less. Adding too many or duplicate dimensions can clutter the drawing and cause mistakes or delays during production. In engineering drawings, a feature can be anything from a hole, a slot, a curved corner, or even a flat face. Dimensions are used to define the size of the feature or its position in relation to other features or reference points, called a datum. Now let's go through some basic rules of dimensioning. When you're adding dimensions to a drawing, it's important to place them where they make the most sense visually and practically. A good rule of thumb is to always dimension a feature where its shape is clearly shown. For instance, if you're trying to show the diameter of a circular hole and it appears as a full circle in the front view, that's the best place to put the dimension. This helps the reader immediately understand what the dimension is referring to. Next, try to keep your dimensions between the views whenever possible. This keeps the drawing neat and prevents overlapping or crowding the main object. However, if there's not enough space between the views, you can place the dimensions outside, just make sure they're still close enough to be clear and not confusing. Now, If your part is going to be joined with another, like using bolts or screws, it's essential to properly dimension the mating features. These are areas where alignment matters, so accurate dimensions help ensure a perfect fit during assembly. You should also avoid dimensioning hidden lines, which are typically shown as dashed lines. These lines represent features not visible in that view, and dimensioning them can lead to misinterpretation. Instead, try to use a different view or even a section view that shows the feature more clearly. When you have multiple related dimensions, don't stack them all in a single line. Instead, stagger them like steps. This not only looks more professional but also makes the dimensions easier to read. Organize your dimensions in a logical way, just like you'd write out instructions, step by step and clear. Finally, always keep in mind how the part will be made and inspected. If a machine tool or measuring device can't easily reach or verify a feature, then you might need to rethink how and where you place your dimensions. Good dimensioning isn't just about what looks right, it's also about what works best in the real world of manufacturing and quality control. When we create a drawing, we are not just showing the shape of an object, we also need to communicate how big it is and where features like holes or edges are located. This is where size and location dimensions come in. Size dimensions describe how big something is. For example, you might show the total width or height of a part, or the diameter of a round hole. These help someone understand the actual physical scale of the object. Size dimensions can be further divided into horizontal dimensions, like width, vertical dimensions, like height, and diameter or radius, which are used for circular features such as holes or round edges. Next, we have location dimensions. These don't tell you how big a feature is, but where it is located. For example, if there's a hole drilled in the middle of a block, the location dimensions would show the distance from the edge of the block to the center of the hole. These are also given in horizontal, vertical, or angular directions, depending on the part's layout. A more structured method of dimensioning is called rectangular coordinate dimensioning, or sometimes baseline dimensioning. In this method, we set an origin point, usually at the lower left corner of the part, and then all measurements are taken from that single reference point. Think of it like using a GPS coordinate system. Instead of measuring from various locations, everything is measured from one known spot. This helps to reduce errors and makes it easier to understand the layout. Let's now go over some standard practices for placing dimensions on technical drawings. This part is very important, not just for making your drawings look neat, but also to make sure your design is clearly understood by the person who needs to build or inspect the part. First, dimension placement depends on the space available between the extension lines. Extension lines are those thin lines that extend from the part's edges to show where the measurement starts and ends. If there's enough space between these lines, the dimension numbers and arrowhead should be placed neatly in between them. This keeps everything compact and easy to read. Now, if you're placing multiple dimensions next to each other, say, several widths or lengths, it's important to group them together and stagger the numbers. Staggering just means that the numbers are placed slightly above or below each other, not all in a straight line, so they don't overlap or get confusing. This gives the drawing a more uniform and tidy appearance. In general, we try to keep dimensions outside the actual object views whenever possible. This makes the drawing look cleaner and prevents the dimension lines from interfering with the object's features. But there are some exceptions. If placing the dimensions outside would require very long extension or leader lines, or if putting the dimension inside the object view actually improves clarity, then it's acceptable to do so. The goal is always to make the drawing as easy to understand as possible. So in short, placing your dimensions carefully, keeping them readable, neat, and logically arranged, is just as important as choosing the correct measurements. These good practices help ensure your technical drawings communicate the design clearly and professionally. When a feature appears multiple times, such as a set of holes arranged in a circular pattern, we use the symbol X to indicate how many times that feature is repeated. For example, 4x diameter 0.375 means there are 4 holes, each with a diameter of 0.375 units. This saves space and keeps the drawing clean, instead of writing the same dimension 4 times. For the case of holes, in technical drawing, whenever we show the diameter of a hole, we must use the diameter symbol O in front of the number. This tells us that the size refers to a circular measurement. You can see this in the image on the right. 040 means the hole has a diameter of 40 units. Also, when you're using a leader line, and you're dimensioning a hole, that line must be radial, meaning it points directly to the center of the circle. Look at the example, the line marked correct goes straight toward the center, while the incorrect one comes in at an angle, which can be confusing and is not standard practice. When dimensioning chamfers, we usually show both the angle and the depth, or length of the flat part. Chamfers are small angled cuts on the edge of a part, often used to remove sharp edges or help with assembly. The same idea applies to internal chamfers, where dimensions indicate how far the chamfer goes and at what angle. Lastly, slotted holes, which are basically elongated holes, need to be clearly dimensioned with length, width, and location. These are important for parts that might need slight adjustment during assembly. So, remember, keeping your dimensions clear, correctly placed, and following these small rules can make a huge difference in how well your drawings are understood. These practices are about more than just neatness, they're about effective communication in engineering and manufacturing. Now, let's move to the ANSI technical drawing views. ANSI stands for the American National Standards Institute, and it plays a big role in making sure engineering drawings are consistent, accurate, and universally understood, especially in industries like manufacturing and design. You can think of ANSI as a guidebook that tells everyone how to draw and read technical drawings in the same way, so there's no confusion when different teams or companies are working together. In engineering and design, we often need to describe three-dimensional objects on two-dimensional paper or screens. This is where ANSI drawing views come in. These views allow us to represent an object from different angles, like the front, top, side, or even a 3D-like isometric view. Each of these views gives us specific information about the shape, size, and features of the object, and together they form a complete picture. They are like different camera angles used in engineering drawings, each one tells us something different about the object. There are several types of ANSI views, and each has a specific purpose. Let's explore the different ANSI technical drawing views one by one. The first and simplest one is the model view. This is just a single view of an object, like the top, front, or an isometric view. Think of it like taking a photo from one angle. If you look at a chair from the front, you can see how tall and wide it is, but you won't see how deep it is. That's the idea of a model view, it gives you a basic idea of what the object looks like. This is often enough for simple parts or early design sketches when we don't need too many details yet. Next, we have the section view. Sometimes we need to know what's going on inside a part, not just outside. This is when section views come in. It's like slicing a cake to see the layers inside, we cut through the part to reveal what's hidden. This is very useful for things like internal holes, channels, or features that you can't see from the outside. Section views can be vertical, horizontal, or even offset depending on where we want to slice through. Next is the broken view, also known as an interrupted view. This is helpful when a part is very long, like a pipe or shaft. If we try to draw the whole length to scale, we'll waste a lot of space. So instead, we break the view in the middle using a zigzag line. This lets us show just the important ends while skipping over the boring middle section. That way, we save space on the drawing sheet but still keep all the necessary details. Moving on to the detail view, this is where we zoom in on a small part of the drawing. Sometimes, features like tiny grooves or threads are too small to see clearly in the main view. Just like you would zoom in on a photo to see something better, we can create a detail view by drawing a circle around the area we want to enlarge. This zoomed-in version helps us show small features clearly and accurately, especially when we need to give precise measurements. Finally, we have the exploded view. This is used in assemblies, where many parts are joined together. In an exploded view, we pull the parts apart slightly and show how they go together. It's like laying out all the components of a bicycle before assembling it. These views are not meant for measurement but for visualization. They are very helpful in instruction manuals, user guides, or to help the assembly team understand how everything fits together. We have now come to the end of our chapter on 2D drawing representation, and hopefully, you're starting to see just how important technical drawings are in the world of design and engineering. In Part 1, we explored the fundamentals of projection. You learned that graphical projection is the technique of representing a 3D object on a 2D surface using lines and planes, no complicated math required. We discussed different projection methods like perspective and parallel, and why parallel projection, especially orthographic projection, is the go-to method for engineers. We also explored the difference between multi-view and axonometric projections, and how first-angle and third-angle systems affect the layout of views. Understanding these basics helps you communicate ideas more precisely and ensures others can read and interpret your drawings accurately. Then in Part 2, we moved into the world of drawing standards and dimensioning. We saw how different countries use different systems like ANSI and ISO, and why it's important to follow a consistent standard. We talked about sheet sizes, drawing scales, line types, and how to properly apply dimensions to your drawings. You also learned about GD&T basics and the different ANSI technical drawing views, such as model views, section views, broken views, detail views, and exploded views, each one helping you tell a clearer story about the object you're designing. Thank you.